Hello, this is the 11th video in my little Fourier series, and we're going to talk about the remainder in this video. We introduced the Fourier series in video 1, which is this, and then in one of the later videos we talked about orthogonality and how it's derived, etc. And it's an infinite sum. But if we stop it at some number, say n, then we call that a partial sum. And if we want to estimate our function f of x with this partial sum, we want to see how close it is. And we can do that by just taking the difference. We call that the remainder. And the closer these two functions are, the smaller this remainder is. And we're going to look at some of the properties of the remainder in this video. Now, some may take the remainder like this, and all the formulas we derived are going to be very similar, but in this video we're going to look at it like this. So there are 6 things we want to prove or show. First one is that this remainder can be written as this integral from 0 to pi, where dn of t is as in video 6, which is the Dirichlet series that we looked at. So this is a Dirichlet kernel. In part B, we're going to show that this remainder can be written like this, where it's an integral from negative pi to pi. And part C, we're going to show that we're going to show that the Fourier series converges to f of x if and only if the integral in a approaches 0. So basically what that means is if this residual goes to 0, well, those two have to equal. And it's one of those, duh moments almost, but we'll show it and prove it. But then, once we know that this residual, if it converges to 0, so that's the only if part. So if the residual converges to 0, well, then we know that the Fourier series converges to f of x. So then we're going to find some, 3 more properties that talk about these residuals, and if these properties happen, then the residual goes to 0 and the Fourier series converges. And then one of those properties is this. We're going to show that the convergence or divergence of the Fourier series corresponding to an integrable function f of x at any point x depends only on the value of f of x in a neighborhood of the point. Now, a neighborhood means like a small area around that point. And so if we're on the real number line, it means a very small interval around that point. And if this is true, so if it only depends upon a small interval around that x, then the series converges. So the next one, part E, is that the Fourier series converges to f of x if and only if for some fixed delta such that it's between 0 and pi, this limit goes to 0. And so what we'll show basically is that when this limit goes to 0, it means this remainder or residual goes to 0. And when the remainder or residual goes to 0, then we know that the Fourier series converges to f of x. That's what this says. And then the last one, part F, which is actually, it's going to look very similar to this, but instead of the Dirichlet kernel, it's going to be some other function. And then we'll show this, that the series converges to f of x if and only if for some delta such that it's between 0 and pi, this integral goes to 0. And again, what this in short means is that if this happens, then the residual goes to 0. And since the residual goes to 0, I keep saying residual, but most people call it a remainder. So if the remainder goes to 0, that means the Fourier series converges to our function f of x. Okay, so let's jump in. So part A is we're going to show that we can write the remainder in sort of a different form. And then it's these two forms, A and B, that we're going to use in parts D, E, and F. Okay, so from F6, which is the Dirichlet kernel, we get this result. So this is f of x. Now if we multiply it by 2 and divide it by 2, that's 1, so we don't change it. And the Dirichlet kernel integrates to 1/2 from 0 to pi. So if we stick in that integral of the Dirichlet kernel here, and then we take those in, which is what this is, then this is f of x. Now F7, which is the partial sum, then we showed that this partial sum can be written like this, as this integral. And then since f of x is this, we put it here. Now we're integrating the same range, so let's just bring it into one integral, factor out the Dirichlet kernel, and we get this. And then that's what we wanted to show. Now part B, we're going to show another way to write the remainder. And here note that we're going from 0 to pi. And here, so from F6 and F7, so that's the Dirichlet kernel and the partial sum. The remainder is this, defined it like this. And then so this can be written like this. And so notice that we're going from negative pi to pi. We showed this formula in part 7 for this. And the Dirichlet kernel, when you integrate from negative pi to pi, is 1. So if we stick in the f of x into this integral of the Dirichlet kernel, it's equal to f of x, because this integral without that goes to, it's 1. And this is not part of the t world. Okay, so now this is the integral over the same range, so let's combine them into one and we get this. And that's what we wanted to show. Now this piece here is going to show up 4 or 5 videos down the road. And I wrote this in a couple weeks after I'd already written this presentation up. And to show that this is true, so they look very similar, right? You just need a U substitution and you can show that. We're not going to prove it, but I'm going to point back to this video to show that, you know, that it can be, that it is true. And it is true. This is equal to that. So this is what we wanted to show in this video. Now part C, we wanted to show that if the Fourier series converges to f of x, that the remainder goes to 0. So here we could subtract that to the other side, and since there's no n to take the limit, we can really think of this as 1, but that's the remainder, and so it goes to 0. And then that's going one way. The other direction is also true. If the remainder is 0, then this is true, and then this is true, and that's true. So it works both ways. So it is an if and only if. Now part D is that we're going to show that the convergence is only, it only matters in a small neighborhood of x. That the Fourier series converges to f of x. So let's fix a delta such that it's between 0 and pi. And from F7, we know that, F7 was the remainder. So we can write the remainder like this. And really this 2, if you bring it in here, that's the Dirichlet kernel. But in F7 that we show this formula. And I'm only partly correct because it's really this, but we integrate from 0 to pi. Then that's the remainder. But we break up that I break up that integral into 2 pieces here. So it's, this is like saying take the integral from 0 to pi, but we did it in 2. And the reason we do that is because of this piece right here. Now we said f is integrable, and so the addition of integrable functions is integrable. Now this piece, the sign, is integrable from pi, or from delta to pi. And so the division of that integral function, it's this is still integrable. Now, if you have an integrable function times sine or cosine, where the coefficient here goes to infinity, so as n goes to infinity, this will go to 0 by the Riemann-Lebesgue theorem that we looked at in video 1. So, to recap, this is an integrable function from delta to pi, and by the Riemann-Lebesgue theorem that we did in the first video, this equals 0 as n goes to infinity. And it's actually kind of neat. I'd recommend graphing several things. Graph several funky integrable functions, take it times sine or cosine, and let this coefficient go to infinity. And it really oscillates so quickly around the x-axis that the area above and below is the same. That's why it integrates to 0. Now, if we look at this piece here, you might say, well, can't we just use the Riemann-Lebesgue theorem and say this goes to 0? And the answer is no, because if you look at 0 here and plug it in here for this denominator, that's 0, and you can't divide by 0. So this function right here, you know, that divided by this part of this, you have to evaluate it. You have to take it, the integral from, say, p to delta, and then let p in limit go to 0 and see if the limit exists to see if that is integrable. And so if it's integrable, of course, then this goes to 0. But the point was that this partial sum really depends upon this piece right here, because this always goes to the 0 by the Riemann-Lebesgue theorem. Okay, so now this shows that the convergence or the divergence only depends upon the interval over the intervals, the integral over the interval 0 to delta, which means that the values of f in the neighborhood of the point x. Okay, so delta is a very small number, and x plus, you know, so this is the t world, so we're going a little above x and a little below x, and so, you know, it's how this behaves. And that's what we wanted to show. Now, part E is we want to show if a condition's met, it means that the series converges. And what I said when we covered E initially is that it's really going to be equivalent to if the remainder goes to 0. Because if the remainder goes to 0, then the series converges. That was what we proved in part C. Okay, so kind of keep that in mind as we go here. So by part C, we know that if the series converges to f of x, the remainder is 0. And the only if part, if the remainder is 0, then the series converges. So we're going to look at this limit of the remainder. Now, by part A, we know the remainder is this. So in part A, it actually kind of looked just like this, but we went from 0 to pi. And so here we broke the integral up from 0 to delta and delta to pi. And we're going to look at these. So now, if this remainder goes to 0, we know that the Fourier series converges. So let's look at this piece here. Now, I claim that by the Riemann-Lebesgue theorem, this goes to 0. And so let's prove that first. So by the Riemann-Lebesgue theorem, the second integral is 0. And here's why. So this is the integral. And then we substitute in what the Dirichlet kernel is. And it's this divided by that, you know, with the 2 in there. So now, f is integrable, and we're dividing by an integrable function, you know, when we're only going from delta to pi. So this is integrable. So as the limit goes to 0, when you multiply an integrable function by sine or cosine, and this coefficient goes to infinity, this is 0, always. And then ultimately, boom, thus the result follows. And what that means is the claim in part E was that if this goes to 0, then the series converges. And we just proved that. And so this part of the remainder always goes to 0 by the Riemann-Lebesgue theorem, this piece. And so if this piece goes to 0, it means the remainder goes to 0, which says the series converges. and we're done. So now in part F, there's another condition that says if it's met, then the Fourier series converges to f of x. And it's going to be the same way. We're going to put some trick on this remainder and show that it goes to 0, which implies this is the case. And if you look at this piece that we just proved for part E, it's going to look like the same thing, but we're going to replace the Dirichlet kernel with something different. And I better flash it just in case. So this is part F that we're going to prove. If this integral is 0, then the series converges. And this is not the Dirichlet kernel. But as I mentioned earlier, it's somehow going to tie into the remainder. If this is 0, then the remainder is 0. And if the remainder is 0, then the series converges. And so we, by part E, and actually we just proved this, that the Fourier series converges to f of x if and only if this part goes to 0. We just showed that. So now, to cut down on the amount of writing that I have to do, we're going to call this junk in here g of t, and that stands for junk. This junk is equal to g of t. Now, by F6, which is the Dirichlet kernel video, this becomes this. So if we put g in here, and that's the Dirichlet kernel, which is this sign over this sign. Of course, the 2 needs to go in there also. That we need to show this. So if this is 0, then it converges, which is equivalent to if this converges, those converge. I mean, if this is 0, it means the remainder is 0, this converges. So let's evaluate this function. But we're going to do it in a tricky way. We're going to look at another function, and it'll all come back in a second. So we're going to develop this function here, 1 of sine over 1/2 t, which is this piece here, minus 1 over 1/2 t. Now, which is this. Now, it can be shown that this function, which is equal to this, is integrable in 0 to pi. And so I'm going to leave that step to you, but it's actually very easy to do, to show that in limit this behaves quite nicely. It goes to 0, and so you can integrate it, so it's integrable. So if we take 1/2, which is integrable, g of t, which is this function of integrable functions, times this integrable function, they're all integrable. So thus, by F1, the Riemann-Lebesgue theorem, this goes to 0, right? Integrable function times sine or cosine, where this coefficient goes to infinity, is 0. Now this is integrable over this range. And really the trick to it is to show that this is integrable. I'm going to leave that as an exercise to you. It's pretty straightforward. So now, so what we do is set this difference in here. We're going to split it into 2. We're going to multiply this times this piece, multiply that times this piece, and then split it into 2. And that's what we do here. So this times this, and then this times this. And this piece here is what star is, okay? So this was part E. This, if the remainder goes to 0, that means this goes to 0, right? So now this piece right here, we just proved definitely goes to 0 by the Riemann-Lebesgue theorem. An integrable function times sine or cosine, where this coefficient goes to infinity, that's 0. Fact. So now this piece is from part E. If this goes to 0, then the remainder is 0, and the Fourier series converges to f of x. But this whole thing goes to 0, so actually this whole piece goes to 0, which says that since we know this goes to 0 and the difference goes to 0, so the limits must be the same, but this limit's 0, so this must be 0. Right? And so that implies that this limit must also be 0. And then we're finished. And that's what we wanted to show, that if this goes to 0, the remainder goes to 0, and the Fourier series converges to f of x. Anyway, I hope you liked that. I did. And subscribe so you don't miss the next one. Thanks. Bye.